Welcome to the BSc 6th semester online classes. Today we shall discuss with the vibrational spectra of beta atomic molecule. In the last class I discussed the rotational spectra of beta atomic molecule and also explained what is that pure rotational spectra and what is diatomic molecule. This vibrational spectra is usually observed in the infrared region of the electromagnetic spectrum. Hence, it is sometimes also called as IR spectroscopy or infrared spectroscopy. This infrared spectroscopy deals with interaction of infrared radiation with matter, especially molecule. The IR spectrum of a compound can be provided an important information about its chemical nature and molecular structure. The spectrum is obtained by measuring the absorption of IR radiation, although infrared emission and reflection are also used. Widely applied in the analysis of organic materials, also useful for atomic inorganic molecules and for organometallic compounds. What is this vibrational spectra? It is also called as harmonic oscillator model because the atoms of a molecule vibrate about their mean position. Hence, they execute a simple harmonic motion. That is, the motion, the vibrations executed by these atoms of a molecule is simple harmonic motion, and it is referred as a harmonic oscillator. The infrared radiation in the range of 10,000 to 100 centimeter raised to minus 1 is absorbed and converted by an organic molecule into energy of a molecular vibration. And this absorption energy is quantized. Hence, it has a definite energy levels. So, according to Hooke's law, the force of repulsion or attraction is directly proportional to the displacement of the particle or atom. Therefore, F is equal to minus F into delta R. So, therefore, we can express this F as a constant which we call it as force constant. A simple harmonic oscillator is a mechanical system consisting of a point mass connected to a massless spring. The mass is under the action of a restoring force proportional to the displacement of the particle from its equilibrium position and the force constant F to the spring. The vibrational energy can be calculated using the classical model of the harmonic oscillator, and that is given by V, which is directly proportional to the displacement, okay, for a particular displacement, that is equal to 1 by 2 k into delta r square, and that is equal to 2 pi square into mu into new oscillation into delta r square, where mu is called as the reduced mass of the system, and that is given by m1 into m2 divided by m1 plus m2 for a diatomic molecule. Using this potential energy function in the Schrodinger equation, the vibrational frequency can be calculated as follows. That is new oscillation, that is equal to 1 by 2 pi into square root of f divided by mu. The vibrational frequency is increasing with increasing the force constant F, increasing the bond strength, and decreasing atomic mass, that is reducer mass. The example for this is the force constant for C double triple bond C is greater than the force constant C double bond C, and which is also greater than a force constant that is C single bond C. Vibrational motion of a diatomic molecule, we shall calculate or we shall derive the expression for the vibrational energy. For that purpose, consider the vibration of a two atom molecule, that means the two particles such as diatomic molecule attached by a spring. The only mode of vibration is expansion and contraction of a spring or a bond between two atoms in the molecule. The extension of the spring is x2 minus x1. Therefore, the restoring force is given by F is equal to minus F into bracket x2 minus x1, where F is called as force constant. The motion can be expressed in terms of Newton's law as follows. That is m into A, where A is called as the acceleration of the atom. So therefore d square x1 by dt square, that gives the acceleration of the first atom. Similarly d2 square x2 upon dt square, that gives the acceleration of the second particle. So the everything is shown in the diagram, in this diagram. Okay, that means the two atoms are moving away or moving towards. Okay, that is the first particle moving away by a distance x1 and moving towards by a distance x1. Similarly, the second particle is also moving away at a distance x2 and moving towards x2. Hence, the displacement is from their mean position is x2 minus x1. And similarly, once they are motion, they definitely possess acceleration. Hence, d square x1 upon dt square is the acceleration of the first, and d2 x square upon dt square, d2 x2 upon d square x2 upon dt square is the acceleration of the second atom. Therefore, we can write the similar equation can be written for the compression also. The solution of these equations show that nu naught is equal to 1 over 2 pi square root of f upon mu, where f is called is a force constant and is given by 4 pi square mu into nu naught square, where nu naught is the fundamental natural frequency of the system and mu is the reduced mass of the two particle system. The fundamental frequency depends on the force constant and the reduced mass of the system. According to the quantum mechanical model, the potential energy curve is given by Vx, that is equal to 1 by 2 F into bracket x2 minus x1 whole raised to square. Take that as equation number 2. On substituting this potential energy in the Schrodinger wave equation and solving that equation, okay, we can get the vibrational energy of a diatomic molecule as EV, that is equal to h nu naught into bracket V minus 1 by 2, where V is equal to 0, 1, 2, 3. So that we call it as the vibrational quantum number, and the frequency is given by that equation number 1. Converting energy into spectroscopic units, that is centimeter raised to minus 1. So that means you have to divide it, that equation number 4 by h into c. Therefore, the energy in terms of centimeter raised to minus 1, so that is given by EV upon hc, or that is equal to V minus 1 by 2 into nu bar, where V is equal to 0, 1, 2, 3 and so on. The different values of vibrational quantum number, the V can be derived from the equation number 5. So when V is equal to 0, then the energy that corresponds to lower energy, that is also called as 0 point energy, that is ZPE. So that is given by E naught, that is equal to 1 by 2 nu bar. And V is equal to 1, that is E1 is equal to 3 by 2 nu bar and so on. So that means the energy difference between successive vibrational levels, that is nu bar only. So that is nu divided by hc, centimeter raised to minus 1. Okay. These levels are equally spaced, that is shown in the figure. For V is equal to 0, the energy is equal to 1 by 2 nu bar centimeter, that is centimeter raised to minus 1. It can be concluded that molecules do not have zero energy. That means atoms in a molecule can never be a completely at rest relative to each other. So in the figure that we have shown, for different vibrational quantum number, the energies the vibrational energy possessed by the molecule, and the spectrum, the transition from V is equal to 0 to 1, 1 to 2, and 2 to 3, and 3 to 4, the energy that corresponds to the values of 0, 1, 2, 3, that is are also given. So that means the curve that represents the potential energy of a diatomic molecule, that is called as harmonic oscillator, and the energy levels are equally spaced. So that is the that means the energy difference between any two vibrational levels is constant. Applying selection rule, that is delta V is equal to plus or minus 1. With the equation number 5, we get, that is the frequency that corresponds to transition V to V plus 1. So that is given by the equation that gives for absorption, and a transition from V plus 1 to V that corresponds to emission. So whatever may be the initial value of V, the transition will give rise to the same energy change, since the vibrational energy levels are equally spaced. Okay. So from these two, absorption equation and emission equation, the energy difference that becomes same, hence the vibrational energy levels are equally spaced. So vibrational spectra gives rise to information regarding the rigidity of the bond. We can calculate the force constant with the help of this vibrational spectra, and also what is the rigidity of the bond that can be determined with the help of that force constant. So with this we shall solve some problems on the pure rotational spectra as well as vibrational spectra of a diatomic molecule. So I already solved the problems on rotational spectra in my classroom. Just you can go through that problems. If you find any difficulty, okay, tomorrow I will engage the online class. In that class we shall discuss in detail. So all these problems that I have already solved in the classroom, just you can go through that one. Even then I am here with providing in the PPT all the problems that I have solved in the classroom, and also the problems as far as concerned to this vibrational spectra. The problem of the, that is number 2, is the molecules of HCl show a strong absorption line of wavelength 3.456 microns. Assuming origin of the line due to vibration, calculate the force constant of our HCl bond. So that means the frequency of vibration is given by nu is equal to 1 over 2 pi square root of k divided by m dash, where m dash is nothing but, in place of mu we can also consider m dash, which is the reduced mass of the system, and also k is given by the equation k is equal to 4 pi square nu square m dash. The mh value, that is equal to 1.0087, that is mass of the hydrogen, and similarly the chlorine mass is given by 35.453. Therefore reduced mass is calculated, and that works out to be 0.98 AMU, and that should be converted in terms of kg by multiplying that AMU by means of 1.67 into 10 raised to minus 27. So that works out to be 1.63 into 10 raised to minus 27 kg. The frequency of vibration is given by nu is equal to c by lambda. Therefore, lambda is already given in the question or in the problem. So with the help of that, where c is the velocity of the electromagnetic radiation, 3 into 10 raised to 8 meter per second divided by the wavelength, that is 3.465 into 10 raised to minus 6. So on calculating this value v, okay, that is frequency nu, okay, and substitute this value of nu in that equation, that is k is equal to 4 pi square nu square m dash, okay, substitute and simplify it. The force constant k works out to be 480 Newton per meter. So similarly, the second problem is given. The second problem is given that the spacing between the vibration levels of a carbon monoxide molecule is 8.45 into 10 raised to minus 2 electron volt. Calculate the value of force constant K of the bond in a CO molecule. So delta E, that is energy difference, that is given. Therefore, this h nu is equal to delta E. So that is equal to 8.45 into 10 raised to minus 2 electron volt. You have to multiply this energy, which is in terms of electron volt, by means of an electronic charge, that is 1.602 into 10 raised to minus 19. So that electron volt will be converted into joules. So therefore, we have nu is equal to this delta E upon H. So where delta E is, that is 8.45 into 1.602 into 10 raised to minus 21 divided by 6.63 into 10 raised to minus 34. So on simplification, that you are getting 2.04 into 10 raised to 13 second raised to minus 1. The reduced mass of the carbon monoxide, that is nu or m dash, that is equal to 1.14 into 10 raised to minus 26 kg. So substitute these values in K, that is force constant, that is given by the equation 4 pi square nu square m dash. So substitute these values of nu square and reduced mass and simplify it. So that works out to be 187 Newton per meter. Similarly, we can calculate the example number 4, okay, and example number 5, okay. If you find any difficulty in solving this 4 and 5, tomorrow we shall discuss. You can ask freely the doubts and questions in the tomorrow's class. So with this, I conclude the molecular spectra, and in the next class we shall completely discuss the Raman spectroscopy. So with this I will conclude my class.